So how do we measure this speckle? The general idea has been shown to you already in the previous course. So you have a laser, which is focused through a lens into the colloidal solution, and you put a detector at angle theta of your choice for the scattering angle, and you focus the scattered light, the light scattered in this direction, on the detector via a lens, and then all what concerns the temporal fluctuation of the intensity is measured and treated by what we call a correlator. So if you look now a bit more into the details of the experiments, first of all, you have to choose a scattering volume, which is defined by the intersection between the incident beam and the beam scattered at an angle theta. And this one needs to be not too large because it is inversely proportional to the coherent area, so the size of the speckle. And if this one is too small, it will be difficult to measure. So typically a good requirement is that you have a volume scattering volume of about a few hundred microns square, which means that you have waste of the beam, incident beam and scattered beam of around 100 micrometer. Moreover, the size determination of the nanoparticle will depend on the angle theta via the diffusion vector Q. And if you don't want to have too much inaccuracy on the size determination, then you don't want to have too large inaccuracy also on the angle of scattering. So you will want to limit the divergency of your beam. So typically a divergency smaller than 1 milliradian is good. And you will have a detection setup, for instance, where you focus the light scattered on a detector which is at the focus point of a lens to really measure the beam that are all parallel to this direction theta. And you also might want to have a small aperture here to limit the divergency also of the detected beam. The first experimental setup of DLS were proposed in the early 70s, where you had here a laser, a lens to focus the laser into the solution, and then the scattered beam was detected at 90 degrees and was also focused via a lens here on a detector. And the reduction of the beam waste and the divergency of the scattered light was performed by putting some apertures, several apertures in a row to really limit the delta theta of the measured signal. A bit more recently, so some 15 years afterwards, there was also a setup that was proposed based on the use of monomode fiber. So here the laser is launched into a monomode fiber, and then there is a lens that collimates the output signal of the monomode fiber. So it creates a parallel beam here that will illuminate the colloidal suspension. And again, the scattered light at 90 degrees is measured via an equivalent system of here a lens that focuses the scattered light into a fiber, and you have an aperture here to limit also the divergency and the waste of the diffused beam. And nowadays you have all sorts of setups, for example, as you can see in the coming movie. Here we are going to show you a setup to do homemade DLS measurements that will come in complement of the theoretical course you have, and we will see some of the issues we can have with such experiments. So when you want to do DLS experiments, you essentially need a laser. We can use some solid state laser, which are very practical. Here we have a green laser which comes out here and is reflected by mirrors to be sent here onto the sample holder. What we do is that we illuminate here a colloidal solution. Here it's a colloidal solution of gold nanoparticles, and when you put them into the light of the laser, you see that you have the laser going through the sample, and here you have the transmitted beam and you see that you have some light here, which is the diffusion of the light by the particles. When you illuminate this colloidal solution, you will see here that you have the transmitted beam that you see going through the cuvette. You see the shadow of the cuvette, and on the side you see some stray light, which is the diffusion by the nanoparticles. As you have seen during the courses, the back scattering here, you also have this back scattering here, and you see that the intensity of the back scattering decreases as a function of the angle of scattering, and it reaches here a minimum around 90 degrees. Now for DLS experiments, what we want to do is we want to detect one part of the scattered light. What we do, usually, we start to put a lens here with a focus point at the center of the sample holder to have more light into the sample. And then we choose an angle of detection. Usually, quite commonly, we choose an angle at 90 degrees because it's the easiest to do, and because it will give a mean size of the nanoparticles that we will see later on. The inconvenience of this geometry is that it is the angle at which the scattered light is the less intense. Okay, so in this geometry, light is scattered in all directions, but we are interested in the light which is scattered here at 90 degrees. Now we need to collect it. To collect it, I take a monomode fiber, and here it's a pigtail fiber, which means that there is here an aspherical lens which will focus all the light that comes from the sample onto the aperture of the fiber. This geometry is interesting because since the aperture here of the lens is small, only the beam that comes very parallel to this this direction will be focused into the fiber. The photons which are diffused with an angle will not reach the entrance of the fiber. And this is interesting because in this way we really fix the angle of scattering to 90 degrees. And this is important to have a very fixed angle because the determination of the diameter we will have afterwards of the size of the nanoparticles depends on this angle. The fiber is then connected to a detector, which is here a photomultiplicator tube. So you send here the photons into this tube, and each photon will be converted into a TTL signal that goes out of the PM into the correlator. This detector needs to be protected from the stray light of the experiment, so we put it under a black curtain. The signal that is detected by the photomultiplicator detector is sent here on a national instrument card via a coaxial wire, and this card will count the number of photons arriving in an interval of time to perform the intensity as a function of time measurements. These counts are then sent to the computer and analyzed via a software. So the photons that are counted by the card are then sent to the computer, and we have a software that will treat the information. So we can here either count the number of counts per seconds, so it's an integrated intensity over time, and then we can stop this counting and start the autocorrelation function. So here the software will perform the autocorrelation function, and the autocorrelation function is displayed during the experiments. On the left here we have the classical autocorrelation function, the intensity autocorrelation function, with a linear scale here on the y-axis. You see that you have an exponential decrease with a baseline which is around 1, as it is predicted by the theory. Here is displayed what we call the electric field autocorrelation function. It is the square root of this function minus the baseline here, and it is represented with a log scale here on the y-axis, and it permits to see where the background of the autocorrelation function arises. And here we see that we have 1, 2, 3, more than 3 orders of magnitude between the signal, the maximum of intensity of the signal, and the occurrence of the background, which is here around 5 to the minus 10. You can also do some DLS measurements under a microscope. For that, you send light onto a sample through the microscope objective. And this objective also measures the backscattered light, which is then focused at the entrance of a monomode fiber. And in this configuration, you do DLS measurements at 180 degrees, so in backscattered configuration. So the laser comes into the microscope at this point. There is here a beam splitter that sends the light onto the sample, which is the little drop you see here. And it is illuminated via the objective. And then the backscattered light is collected here and focused by a lens, which is here, to the entrance here of the monomode fiber. And this goes to the detector. So the light is focused at the entrance of the fiber. And part of the scattered light is also sent via a beam splitter, which is here, to a camera to observe the sample on the computer. What we see here is the scattering of the nanoparticles, which are in solution. And you see that there are fluctuations of the intensity because the nanoparticle move in a Brownian motion. And this is the intensities we are going to analyze in DLS.
Okay, so once you have sent the light onto the detector, you have to focus on the autocorrelation part, and so on the temporal fluctuation of this intensity. So the detector here will convert each photon that comes to the detector into a TTL signal, which is the square or rectangular signal. And the later are sent onto an electronic card that has an internal clock, which permits to treat the signal and to either measure the time delay between the arrival of 2 photons if the intensity is weak, or to measure the number of photons arriving during a time delay which is fixed by the experimentalist. In any of these 2 cases, you have a set of data, either of time delay or of number of counts arriving during a delta delay of time delta t. And these data are sent to a computer where a software will reconstruct the time-dependent intensity of the signal, either by summing the time delay or by summing the number of counts per delta t. And then the software will compute the autocorrelation function, and you get this type of curves as an output of your experiment. Okay, so let's summarize a little bit. As you have seen in the course, you have Brownian motion of your nanoparticles. They create some fluctuation in the intensities which is scattered at a point. And the frequency of these fluctuation depends on the size of the nanoparticle. So when you plot and calculate and plot the autocorrelation function of these intensities, you have a curve with a time delay which is small for small particles and bigger for bigger particles. And usually when you use, for instance, a commercial setup or a setup that you have not built yourself, from these measured autocorrelation function, you have access to the distribution of size of your nanoparticle, which is the information you're looking for when you do such experiments. So what we'll see now in the rest of this course is how do we go from this part of the experiment to this type of result? How do we analyze these curves to obtain the size distribution of the nanoparticle? So first of all, we will examine the case of a monodisperse colloidal solution. That means that we consider a solution where the nanoparticles are all spherical and all have the same size. And in that case, the model for DLS tells us that the autocorrelation function takes this expression where you have an exponential with the time decay, gamma. Gamma, in fact, is inversely proportional of the time decay. And this gamma is equal to d times q squared, where d is the diffusion coefficient of the nanoparticle related to its size, so to its introdynamic diameter, and Q is the diffusion vector, which is fixed by the experimental conditions. So once you have measured your experimental autocorrelation function, you will perform a fitting of this data via, for example, a least square fitting procedure, where you will fit this data using this expression with A, gamma, and B being the variables of the fitting. When your fit comes to convergency, you have a good agreement between the fits in blue here and the data in black. And this convergency occurs for values of A and B, and most importantly, for a value of gamma, from which you can calculate D, and from which you can calculate the hydrodynamic diameter of your particle. So this is how you obtain the radius of your particle from the autocorrelation function. So let's look how we can do that when we perform an experiment. Let's now consider that you have measured such an autocorrelation function and you want to fit it to obtain the diameter of your nanoparticles. So in the first case, we're going to use the monodisperse equation, which is given here by the exponential decay. And you can make a fit using a least square fitting procedure that you have integrated in most of the software you can use to do some data plotting. So we choose here an exponential decay. And when the convergency is obtained, you get this fit in red, which shows quite a good agreement with the data, except for some points here. And you can display the parameters which have been used by the software to calculate this this fit, and you find the different elements A, B, and gamma that you want to calculate from this fitting. Once you have obtained these parameters, you use the value of gamma to obtain the diameter of the nanoparticles simply by using this relation where Q2 and D can be calculated using this formula. So the diffusion vector Q2 is calculating using the experimental condition parameters. So the diffusion, the scattering angle, the wavelength of the laser, and the refraction index of the solvent, which is here water. And for D, it depends on the diameter of the nanoparticle, but also on values of the viscosity of the solvent at the temperature, at the working temperature, the temperature, and the Boltzmann constant. So you get this very simple formula, and you can calculate D from gamma. Now, as we said before, there is some discrepancy here between the fit and the data. And this comes from the fact that the autocorrelation function we have measured is not, strictly speaking, an exponential decay. And this, as we will see in the following, comes from the fact that you have a certain distribution of size of your nanoparticle in your sample.